Tonight, while most people will be sleeping, an object from outside our solar system will pass Jupiter's gravitational boundary with a margin of error smaller than a rounding mistake. It is carrying deuterium, the same fuel humanity has spent 70 years and hundreds of billions of dollars trying to harness for nuclear fusion. New James Webb data shows isotope ratios 10 times higher than any comet ever measured in our solar system. Harvard says the math is broken. Nobody is explaining the anti-tail pointing directly at the sun. Stay with me until the end of this video, because what we find out tonight either changes everything or raises questions we're not ready for. The mystery is still open, the data is still coming in, and the answer to whether something impossibly precise, impossibly fueled, and impossibly timed just threaded Jupiter's gravitational boundary by accident, or not, is closer than it has ever been. Hit subscribe and follow along, because this is one of those rare moments when the cosmos does something unexpected and we get to be the generation that was watching when it happened. Part 1. Tomorrow's flyby, the most precise coincidence in the solar system. Something is coming. Right now, at this exact moment, an object from outside our solar system is threading a gravitational needle with a precision that has left some of the world's best orbital mechanics researchers quietly setting down their coffee and staring at their screens. Not because the numbers are wrong, because the numbers are too right. The object is called 3I Atlas. It is the third interstellar visitor ever confirmed in recorded human history, and in less than 24 hours, it will make its closest approach to Jupiter at a distance of 53.6 million kilometers. That number probably means nothing to you right now. Give it 30 seconds. Jupiter has what astronomers call a hill radius. Think of it as a gravitational fence, the boundary where Jupiter's own gravity stops competing with the Sun and starts winning. Objects that pass inside that fence get dragged into Jupiter's sphere of influence. Objects that stay outside it keep moving on their own terms. Jupiter's hill radius is approximately 53.5 million kilometers. The flyby distance is 53.6 million kilometers. That is a margin of roughly 100,000 kilometers. On the scale of the outer solar system, that is nothing. That is the width of a human hair held up against a football stadium. We have always believed that coincidences happen in astronomy. Planets align, asteroids brush past moons, comets graze the edges of rings. But there is a specific kind of coincidence that stops being comfortable when you sit with it long enough. This one is starting to make people uncomfortable. Imagine throwing a marble from one side of a city at a target on the other side, and that marble skims the exact outer edge of the target without touching it. Not through the target, not missing by a mile, exactly the edge. That is what we are watching happen tomorrow. 3I Atlas was first detected by the Atlas Survey Telescope system, which is why it carries that name. When its orbit was computed and astronomers realized it was moving on a hyperbolic trajectory, meaning it came from outside our solar system and will leave and never return, it joined an extraordinarily exclusive club. The first confirmed interstellar object was 1I/Oumuamua, discovered in 2017. Then came 2I/Borisov in 2019. The gap between the first and second was about 2 years. The gap between the second and the third was shorter still. Whether that means we are getting better at looking, or there is simply more to find, is a question worth holding on to. What we knew about interstellar objects before 3I Atlas was already enough to generate arguments at conferences. Oumuamua was weird, cigar-shaped or pancake-shaped depending on who you asked, tumbling, accelerating in ways that gas outgassing alone struggled to fully explain. Borisov was more normal, more comet-like, and in some ways, reassuring. 3I Atlas appeared initially to be in Borisov's camp, a big active interstellar comet. Interesting, historic, probably explainable. Then the James Webb Space Telescope looked at it. 2 papers dropped in rapid succession from independent research teams. Both focused on the water vapor surrounding the nucleus of the object. Both measured the same thing, the ratio of deuterium to regular hydrogen in that water. Deuterium is sometimes called heavy hydrogen. It has 1 extra neutron in its nucleus compared to normal hydrogen, which makes it slightly heavier, slightly different in how it behaves chemically and physically. You already know deuterium, even if you did not know the name. It is the fuel that experimental nuclear fusion reactors on Earth are trying to harness. It is why projects like ITER exist. It is the substance that, if we ever crack fusion power, will likely run the civilization of the future. Typical comets from our own solar system have deuterium to hydrogen ratios of around 0.02 to 0.05%. Earth's oceans sit at about 0.0156%. These are the numbers we have measured across dozens of comets over decades of observation. They cluster together in a range that makes chemical and physical sense given how our solar system formed. 3I Atlas measured at roughly 1%. That is not a small deviation. That is not a rounding error or a calibration issue. That is 10 to 50 times higher than anything we have ever measured in a solar system comet. 1 in every 100 hydrogen atoms in the water surrounding this object is the heavy variant, the fusion fuel variant. And right now, that object is gliding toward Jupiter's gravitational boundary with the precision of something that knew exactly where the line was. Maybe it is an ancient comet. Maybe the chemistry makes sense in ways we have not fully worked out yet. Harvard's Avi Loeb, who has spent several years publicly arguing that scientists are too quick to dismiss anomalies in interstellar objects, has compiled 22 separate irregularities associated with this object. 22. He is not claiming it is alien technology. He is saying the mainstream explanation has mathematical problems that deserve serious attention, not polite dismissal. And that is before we get to the anti-tale. There is a feature in the telescope images of 3I Atlas that researchers have been careful about discussing publicly. A structure extending hundreds of thousands of kilometers from the nucleus, collimated like a beam pointing directly at the sun, the exact direction that solar wind should make impossible. A structure that persisted not for hours, not for days, but for months. The flyby is tomorrow. But the question started the moment we looked closely enough to see them. And now that you know what to look for, you are not going to be able to unsee any of it. Part 2. The deuterium problem. Why the chemistry makes no sense. The number 1% does not sound dramatic until you understand what it costs to make it. Deuterium is not randomly distributed across the universe. It forms preferentially in specific conditions: extreme cold, isolation, time. The process is called isotopic fractionation, and it works like this. At temperatures close to absolute zero, chemical reactions that would normally proceed in both directions start to prefer one direction. Deuterium gets locked into molecules more efficiently than regular hydrogen does when the environment is cold enough. The colder the environment, and the longer it persists, the higher the deuterium enrichment you eventually get. When astronomers saw the deuterium ratio in 3I Atlas, the temperature implied by that ratio was below 30 Kelvin. That is negative 243 degrees Celsius. That is not the temperature of space between planets in our solar system. That is the temperature of a cold molecular cloud, the dense, frigid nurseries where stars are born scattered across the galaxy. To understand why that matters, you need a brief detour through time. Our solar system formed 4.6 billion years ago. The Milky Way itself is approximately 13.6 billion years old. Stars existed long before our Sun. Many of them formed in early epochs of the galaxy, when conditions were radically different from today. The interstellar environment was less enriched with heavy elements. The molecular clouds were colder in many regions. Some researchers looking at the deuterium signal in 3I Atlas have suggested that the chemistry is consistent with an object that formed 10 to 12 billion years ago in the early Milky Way, when our Sun did not yet exist. Sit with that for a moment. An object potentially twice as old as our solar system. An object that formed when the galaxy was still young, drifting through interstellar space for longer than Earth has existed, and has now arrived here, threading Jupiter's gravitational boundary, loaded with fusion fuel. If that does not do something to your sense of scale, check your pulse. But here is where the puzzle turns genuinely strange, and why some astronomers are using words like paradox out loud at conferences. If the object formed in the early Milky Way, in a metal-poor environment, meaning an environment deficient in elements heavier than hydrogen and helium, then its chemistry should reflect that poverty. Early stars produced very little carbon, oxygen, nitrogen, or anything on the periodic table beyond the lightest elements. The universe needed generations of stellar explosions to cook up the heavier stuff and scatter it into space. Yet the gas plume surrounding 3I Atlas is chemically rich. The James Webb observations and supporting data from other observatories detected carbon dioxide, methanol, methane, and complex organic molecules. These substances require carbon and oxygen. They require elements that in a genuinely primordial environment should barely exist. You cannot have abundant methanol in a system that lacked carbon. You cannot have complex organics if the raw ingredients were not there to begin with. So we appear to have an object with deuterium ratios consistent with formation in an extremely cold, extremely old, metal-poor environment, carrying chemistry that requires the ingredients of a metal-rich environment. These two things are fighting each other. Astronomers like a mystery, but they generally prefer mysteries with one clean resolution. This one has at least 3 competing explanations, none of which are fully satisfying. The first possibility is unusual formation chemistry. Perhaps some process in early molecular clouds could have produced this particular mix in ways our models do not yet capture. The second possibility involves contamination. Perhaps the object spent billions of years drifting through space and accumulated a chemical veneer from later collisions with other material, masking its primordial interior beneath a newer surface. The third involves internal processing. The idea that long exposure to cosmic rays and solar radiation has transformed the original chemistry from the inside out. Each of these has problems. Internal processing of this magnitude would also degrade the deuterium signal, not preserve it. Contamination would need to be extraordinarily uniform to explain the observations, and unusual formation chemistry is, in scientific terms, a placeholder answer, a way of saying the models need more work without specifying what that work will find. What makes this especially hard to dismiss is the precision of the measurements. The James Webb Space Telescope is not guessing. Its infrared spectroscopy is the most sensitive tool humanity has ever pointed at the sky. When it reads a deuterium ratio of approximately 1%, that is not noise. That is signal. And signal in astronomy is supposed to mean something. Here is the question that keeps surfacing in the papers, in the conference hallways, in the cautious language of researchers who choose their words carefully. What natural process reliably produces deuterium enrichment, this extreme in a body that is also chemically complex and moving through space on a hyperbolic trajectory? We do not have a clean answer. We have hypotheses, we have models, we have uncertainty. What we also have, apparently, is a jet pointing directly at the sun, and nobody builds a jet pointing at the sun by accident, unless nature has a trick we have not learned yet. Part 3. The anti-tail nobody wants to talk about. Every comet wears 2 tails, and both of them point away from the sun. This is not a coincidence. It is physics. The first tail, made of dust, gets pushed by the gentle but persistent pressure of sunlight. The second tail, made of ionized gas, gets blasted backward by the solar wind, the constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Comet tails are nature's windsocks, and the wind always blows away from the sun. That is why, as a comet moves through the sky, its tails always trail behind it in a direction we can predict. This has been confirmed across thousands of observations spanning centuries of astronomy. So, when Hubble Space Telescope images of 3I Atlas revealed a structure extending hundreds of thousands of kilometers directly toward the sun, the reaction in certain parts of the astronomical community was not excitement. It was something quieter, something closer to the specific unease you feel when a door you thought was locked is standing slightly open. To be fair, anti-tails are a known phenomenon. They appear occasionally in comets observed from Earth, and for decades astronomers have explained them without drama. When Earth's orbital plane intersects the dust trail of a comet at just the right angle, perspective can make some of the dust appear to project forward toward the sun. It is an optical illusion, a trick of geometry, not a real structure. Researchers confirmed the mechanism behind anti-tails like Comet Kohutex in 1973, and the explanation satisfied everyone. But this explanation requires the feature to be virtual, a projection artifact, not a real physical extension. And the structure observed in 3I Atlas does not behave like a projection artifact. The feature persisted for months. Projection artifacts are sensitive to orbital geometry. As the comet moves and Earth's viewing angle changes, the apparent anti-tail shifts and eventually disappears. This one did not disappear. It maintained its sunward orientation through multiple observation windows, through different telescope platforms, through the object's closest approach to the sun and back out. When the object passed perihelion, its closest point to the sun, the feature did reverse its orientation relative to the object's direction of motion, but it kept pointing toward the sun. The structure is also collimated. Real anti-tails created by perspective are diffuse. soft-edged, gradually fading into the surrounding coma. This feature is narrow, it holds its shape. Collimation, the property of forming a tight focused beam rather than spreading out in all directions, is not a property of passive dust drifting in space. Passive dust spreads. Focused structures require either a focusing mechanism or an extremely specific geometry of release, or something actively directing the material. Now, there is a natural explanation on the table. Large dust particles, much larger than the sub-millimeter grains typical of comet tails, can resist solar radiation pressure enough to travel in unusual directions. If 3I Atlas ejected particles large enough, those particles could travel on orbits that, from our vantage point, appear to point toward the Sun. This is a legitimate mechanism. It is physically coherent. The problem is mass. To produce the observed brightness in a collimated structure of that size using large particles, you need an extraordinary amount of mass. The calculations push into numbers that challenge what a comet nucleus of this estimated size could plausibly contain and release. You end up needing a mass budget that the object does not obviously have, and we will come back to mass budgets, because they are going to cause us problems more than once in this story. Some papers describe the feature as an unusual jet geometry, meaning it might be a jet of material directed sunward by specific topographic or compositional features on the rotating nucleus. This is a more tractable explanation in some ways. Irregular comet surfaces can create jets that appear to point in unexpected directions when combined with rotation dynamics. But sustaining a sunward jet of this brightness and collimation for months requires sustained active outgassing at a very specific orientation that survives for far longer than most cometary jets maintain their geometry. The mainstream scientific literature has not settled on an explanation. Multiple papers describe the feature, characterize its properties, and stop short of a mechanism. That is not a scandal. Unresolved features are normal in active research, but the combination of duration, collimation, and sunward orientation places this feature in territory that existing models handle awkwardly. And then someone looked more carefully at the processed Hubble images. They applied a specific image processing technique designed to reveal hidden structure in comet comae. And what they found was not one anomalous feature, it was three. Part 4. The three-jet thruster pattern. There is a technique in comet astronomy called the Larsen-Secunina filter, named after the researchers who developed it in the 1980s. The method works by subtracting the smooth, symmetric glow of a comet's coma, the diffuse cloud of gas and dust surrounding the nucleus, from the raw image. Once that uniform background is removed, asymmetric structures hidden within the brightness become visible. Jets, streamers, fans of material that would otherwise be washed out by the surrounding glow resolve into clear features. When researchers applied this technique to Hubble images of 3I Atlas, 3 jets appeared. Not 2, not 4, 3. And they were separated from each other by approximately 120 degrees, arranged around the nucleus in a configuration of perfect triangular symmetry. 3 evenly spaced structures, 120 degrees apart, each extending outward in a different direction from the same central body. Let us be precise about what the natural explanation for this looks like. Comet nuclei are not smooth spheres. They are irregular, fractured, porous objects with varied surface compositions. When solar heating reaches volatile-rich regions, pockets of ice or frozen gases near the surface, those materials sublimate rapidly and produce jets of escaping gas and entrained dust. Irregular surfaces can produce jets at odd angles. Multiple active regions can produce multiple jets simultaneously. There is nothing in the laws of physics that forbids 3 active regions on a comet nucleus. But 3 active regions spaced exactly 120 degrees apart. That specific geometric arrangement is unusual. Natural distributions of volatile pockets on comet surfaces are irregular. They follow the history of the nucleus, impacts, fractures, compositional gradients accumulated over billions of years. They are not known to produce evenly spaced, rotationally symmetric, active regions as a standard outcome. When you see perfect triangular symmetry in nature, it usually means one of 2 things. Either a physical constraint is forcing the symmetry, or you're looking at something that was constructed with symmetry in mind. The first option is the one science is working on. 3 evenly spaced jets could, in principle, arise if the comet's rotation axis is oriented in a way that causes 3 longitudinally distinct regions to receive equal solar heating. Early measurements suggested that the rotation axis of 3I Atlas was tilted within 8 degrees of the direction toward the Sun, meaning the Sun was heating the nucleus almost directly along its pole. That orientation could, under specific modelling conditions, produce symmetric jet activation. Several researchers have published models exploring this configuration. What makes the 3-jet pattern difficult to fully explain away is stability. The jets persisted across multiple observation epochs spanning months. Cometary jets driven by solar heating change as the comet's orientation to the Sun evolves, as volatile regions become depleted as the surface shifts. Long-duration stability in jet geometry is not the norm. It requires either an unusually stable rotational state, unusually deep and sustained volatile reservoirs, or something maintaining the jet positions in a way that does not depend on the usual mechanisms. A.V. Loeb, the Harvard astronomer who has made the study of anomalous interstellar objects something of a professional mission, collected this jet pattern as one of his 22 documented anomalies. He is careful, very careful, to avoid claiming any specific conclusion. His position is methodological. When an object displays 22 statistically unusual properties simultaneously, the probability that all of them are independent coincidences requires examination. He does not say it is alien technology. He says the mainstream explanation is under mathematical strain and that the field deserves more rigorous scrutiny. Some voices in more speculative corners of online science commentary have drawn a very specific comparison. 3 jets, separated by 120 degrees, maintaining stable operation for months on an object with anomalous chemistry and a trajectory that threads Jupiter's gravitational boundary. The word thrusters has appeared in comment sections, podcasts, and a handful of preprint papers that the mainstream community has not embraced. To be absolutely clear, there is no evidence, no confirmed data, no peer-reviewed finding that supports the conclusion that these jets represent propulsion technology of any kind. The idea is speculative in the strictest sense of that word. But here is the thing about speculation. When the mainstream models are under strain, when the data is genuinely unusual, when multiple independent anomalies cluster around the same object, speculation is not irresponsible. It is the beginning of the next question, and the next question, in this case, involves a number so large it breaks the math. Part 5. The mass budget that breaks the comet theory. Astronomy has always been comfortable with big numbers, distances in light years, masses measured in solar units, timescales in billions of years. The field runs on quantities that require scientific notation just to write down. But there is a specific kind of big number that makes astronomers uncomfortable. It is the kind that comes out of a calculation and does not agree with what you observe. The mass budget problem with 3I Atlas starts with a simple question. How common are interstellar objects? Before 2017, we had detected 0. Then we found Oumuamua, then Borisov, then 3I Atlas within roughly 8 years. Statistical reasoning is straightforward here. If 3 objects have passed through the observable solar system in 8 years, the true population drifting through the galaxy must be enormous. Our telescopes only see a fraction of the sky at any given time, only down to certain brightness thresholds, only within a limited distance range. Correct for all of those observational biases, and the implied population of interstellar objects is in the billions per cubic light year of space. That is fine. Space is large. Billions of objects per cubic light year sounds impressive until you remember how much volume there is to fill. The problem is where those objects came from. The leading model is that interstellar objects are planetary system debris, material ejected during the formation of planetary systems. When young solar systems form, gravitational interactions between growing planets sling enormous quantities of smaller bodies out of the system entirely. Our own solar system ejected material this way. The Oort cloud, the vast spherical reservoir of comets at the outer edge of the solar system, contains objects that nearly escaped, and objects that did escape must be even more numerous. To produce the observed number of interstellar objects in the galaxy requires that the average stellar system eject truly enormous quantities of material. Loeb's calculations, which have been published and critiqued and defended in the literature, suggest each stellar system would need to have ejected on the order of 1,000 Earth masses of objects in the relevant size range for 3I Atlas. 1,000 Earth masses. To put that in context, the entire current population of asteroids and comets in our solar system's inner regions amounts to a small fraction of one Earth mass. The The Kuiper belt, the outer disk of icy bodies beyond Neptune, contains perhaps a few tenths of an Earth mass of material. The math requires systems to have ejected far more than we think they typically contain. Now, some astronomers push back hard on this. The calculation involves uncertain assumptions at every step. The detection efficiency of current surveys, the size distribution of interstellar objects, the fraction of systems that undergo the ejection events needed. Tweak any of those variables within plausible ranges and the required mass per system changes significantly. The critics are not wrong that the uncertainty is real, but the chemical composition problem compounds the mass budget problem in a specific way. 3I Atlas, remember, shows deuterium enrichment consistent with an extremely old, cold, metal-poor origin environment. Early stellar systems in the Milky Way had planetary disks with very little carbon, very little oxygen, very little of anything heavier than helium. Yet the gas plume of 3I Atlas contains methanol, carbon dioxide, methane, and complex organics, all of which require those heavier elements. So either the object is not from the primordial early galaxy despite its deuterium signature, which requires explaining why the deuterium ratio is so extreme, or it is from the early galaxy and accumulated its complex chemistry from collisions later, which requires specifying a mechanism for uniform chemical contamination across the entire observable surface, or the models for early planetary system chemistry are substantially wrong. 3 different explanations, 3 different sets of problems, all converging on the same object. An object that, by the way, is not travelling through space in a straight line. Something is pushing it sideways, and it has been doing that for months. Part 6. The sideways acceleration problem. Comets move through space according to rules. This is one of the genuinely satisfying facts about orbital mechanics, that objects moving under the influence of gravity follow paths that can be calculated with extraordinary precision using mathematics developed 3 centuries ago, refined by 2 centuries of telescopic observation, and now implemented in software that tracks thousands of solar system objects simultaneously to accuracies that would have seemed supernatural to the astronomers who laid the theoretical foundations. Newton's laws, Einstein's corrections to them for objects moving fast or near massive bodies, and the accumulated observational data of generations of skywatchers combine to produce trajectory predictions that are, for well-behaved objects, accurate to fractions of a kilometre over timescales of years. Gravity from the Sun dominates at the scale of the solar system, bending every orbit into a conic section, circle, ellipse, parabola, or hyperbola depending on the object's speed relative to the local escape velocity. Gravity from the planets perturbs those paths with a precision that has been calculated, measured, and confirmed to extraordinary accuracy. Even the slow, gentle pressure of sunlight, photons carrying momentum, transferring tiny pushes to every surface they strike, is accounted for in high-precision orbital models under the name radiation pressure. These forces are understood. Their combined effect on any given object can be calculated, and when an object's observed position deviates from the position that calculation predicts, the deviation is not ignored. It is measured, characterized, and handed to the next level of the modelling framework, which asks, what additional force is acting on this object, in what direction, and at what magnitude? For comets, the answer to that question has a standard and well-validated form: gas jets. When solar radiation heats the surface of a cometary nucleus, volatile materials, water ice, carbon dioxide, carbon monoxide, methanol, and dozens of other species depending on the composition of the nucleus, sublimate. They transition from solid to gas and escape from the surface into space. That escaping gas carries momentum. By Newton's third law, the reaction to that momentum transfer pushes the nucleus in the opposite direction, exactly as rocket exhaust pushes a spacecraft. The effect is tiny for any individual molecule leaving the surface. Accumulated across the billions upon billions of molecular departures occurring every second from an active comet nucleus, the effect becomes measurable. Over days and weeks, those tiny pushes add up to trajectory deviations that, without correction, would cause predictions to miss the object's actual position by thousands of kilometres. The standard model for this non-gravitational acceleration works well. It was developed by Brian Marsden and colleagues in the 1970s and has been refined through decades of application to hundreds of comets. The model parameterizes the non-gravitational force as a function of the comet's distance from the Sun, larger when the comet is closer and outgassing more vigorously, smaller when it's farther and the volatile release rate drops. The direction of the force in the standard model is predominantly radial, pointing away from the Sun, which is the direction you expect if the jets are driven primarily by solar heating, and the active regions are distributed broadly enough across the sunward hemisphere to produce a net anti-solar thrust. 3I Atlas has non-gravitational acceleration. Every active comet does, and its presence in the trajectory data of an interstellar comet is neither surprising nor alarming in itself. The fact that an object producing the prodigious quantities of gas and dust observed in 3I Atlas would push itself off a purely gravitational path is entirely expected. That part of the story is boring. The boring part ends when you look at the direction. The acceleration measured in 3I Atlas has a component that is transverse, sideways relative to the radial direction connecting the object to the Sun. Something is pushing it at an angle that is not simply away from the Sun, not simply along the radial direction that standard solar heating-driven outgassing would produce. The push has a sideways element, not a tiny, barely detectable sideways element that sits at the edge of measurement uncertainty and might disappear with better data. A measurable, persistent, characterizable transverse component that has been tracked across multiple observation arcs spanning months, and that remains present in the data regardless of which research team is doing the analysis. This is the same class of trajectory anomaly that made Oumuamua so controversial. Oumuamua's non-gravitational acceleration was also in a direction that standard outgassing models struggle to explain, and the object produced no detectable coma, no visible gas release that could anchor the standard model to an observed physical process. The controversy that followed generated dozens of papers, several competing natural explanations, and at least one high-profile proposal of a non-natural explanation that the mainstream community rejected without quite managing to fully refute. Oumuamua's acceleration anomaly remains technically unresolved in the sense that no single explanation has achieved consensus, though the hydrogen outgassing model proposed by Darryl Seligman and Gregory Laughlin in 2023 has attracted substantial support as the most physically coherent natural candidate. For 3I Atlas, the situation is different in an important way. Unlike Oumuamua, 3I Atlas is visibly, prodigiously active. It has a coma, it has jets, it has measurable outgassing rates for multiple molecular species. The standard model therefore has something to work with. There is an observed physical process to which the non-gravitational acceleration can in principle be anchored. The question is whether the observed outgassing in the configuration the jets appear to occupy can quantitatively account for both the magnitude and the direction of the measured acceleration. And that question is genuinely hard to answer, for reasons that are intrinsic to the physics of the system, rather than to any deficiency in the available data. The natural explanation for transverse acceleration involves complex jet geometry on a rotating nucleus. If the active jets on the nucleus are not symmetric around the rotation axis, if they are offset, if they fire from regions that are not evenly distributed in longitude around the nucleus, then the geometry of a rotating body with asymmetric jets can produce net acceleration components in directions other than purely radial. As the nucleus rotates, each jet sweeps through an arc. If the jets are not symmetric, the time-average thrust from that rotation has components in multiple directions, including transverse to the Sun-comet line. This is legitimate, well-understood physics. It is not a special pleading or an ad hoc mechanism invented to rescue the natural explanation. Multiple research groups have constructed models incorporating asymmetric rotating jets and shown that transverse acceleration can, in principle, result. The difficulty is in the details of the specific case. The magnitude of the transverse component measured in 3I Atlas, combined with its persistence over months of observation, requires a specific jet configuration, specific locations, specific orientations, specific activity levels that must be maintained with unusual stability for the effect to accumulate in the way the data shows. And the system is coupled in ways that make this stability hard to produce naturally. As the nucleus outgasses, it loses mass. Losing mass changes the moment of inertia of the nucleus. Changing the moment of inertia changes the rotation rate and rotation axis orientation. Changing the rotation changes the geometry of how the jets fire. Changing the jet geometry changes the non-gravitational acceleration pattern. The system is not static, it is continuously evolving, and the evolution should, in natural comets, produce a changing acceleration profile rather than a persistent one. Researchers working on modelling this system acknowledge the difficulty openly and without apparent discomfort, because acknowledging that a problem is hard is simply the accurate description of the situation. It is not a concession that the problem is unsolvable or that the natural explanation is wrong. Hard problems get solved, models get refined, parameters get better constrained as more data arrives. The transverse acceleration of 3I Atlas may well receive a complete and satisfying natural explanation within months of the Jupiter flyby, once the post-encounter trajectory data provides the tightest constraints yet on the non-gravitational force vector. But here is what remains true regardless of how that explanation eventually develops. The motion of 3I Atlas does not fit a simple passive comet model. Something beyond straightforward solar heating-driven radial outgassing is contributing to its trajectory in a measurable and persistent way. That contribution has been present and detectable across every observation arc the field has collected since the object's discovery. It is not a transient spike associated with a specific outgassing event. It is a consistent feature of the object's dynamics, operating continuously, carrying a body loaded with anomalous deuterium, anomalous methanol, anomalous nickel-ion ratios, and 3 symmetrically arranged jets toward the most precisely threaded gravitational boundary approach in the history of interstellar object observation. The phrase propulsive acceleration has appeared in connection with this object in speculative commentary, podcasts, and at least a handful of preprint papers that have not navigated peer review successfully. The peer-reviewed literature does not support the conclusion that the acceleration is intentional or controlled. What the peer-reviewed literature does support, what Loeb himself has argued in publications that have survived review, is that the combination of anomalies clustering around this single object warrants investigation that goes beyond the standard comet model, not because the standard model is certainly wrong, but because the standard model is under sufficient strain across sufficient independent measurements that intellectual honesty requires acknowledging the strain rather than smoothing over it. That is a methodological argument. It is not an extraordinary claim. The extraordinary claims exist, and they have a devoted audience, and some of them involve a radio telescope that picked up something impossible 47 years ago and never heard it again. Part 7. The Methanol Factory. Somewhere between Jupiter and the Sun, an interstellar object is producing methanol at a rate that makes chemists uncomfortable. Not alarmed, not panicked, just quietly, professionally uncomfortable in the way that scientists get when a number comes back from an instrument and refuses to fit neatly into any of the boxes the field has spent decades carefully constructing. Methanol is not exotic. It is one of the simplest alcohol molecules in the known universe, 1 carbon atom bonded to 3 hydrogen atoms and 1 hydroxyl group, a molecular structure so straightforward that undergraduate chemistry students encounter it in their first semester. Its chemical formula is CH3OH. It has a molecular weight of 32 atomic mass units. It smells sharp, burns with a nearly invisible flame, and is toxic to humans in quantities that would fit in a shot glass. On Earth, it is an industrial solvent, a fuel additive, a feedstock for chemical manufacturing. In space, it is something considerably more interesting, one of the most widely distributed complex molecules in the interstellar medium, a chemical signature that appears wherever the right conditions, cold temperatures, carbon monoxide, hydrogen, and an energy source to drive reactions come together over sufficient time. Methanol forms naturally in space through reactions between carbon monoxide and hydrogen on the surfaces of cold dust grains. The grains act as tiny reaction platforms, providing surfaces where molecules that would never encounter each other in the gas phase can meet, bond, and build complexity. Ultraviolet radiation from nearby stars and cosmic ray bombardment from throughout the galaxy provide the energy to drive those reactions forward, even at temperatures close to absolute zero. The process is slow by human standards and extraordinarily productive by cosmic ones. Given enough time, the cold surfaces of interstellar dust grains accumulate layers of ice that are chemically rich in ways that still surprise researchers who study them. We find methanol in molecular clouds, in the collapsing envelopes of forming stars, in the protoplanetary disks where planetary systems are being assembled, and on the surfaces of comets and asteroids throughout our solar system. Methanol is, in the Cosmic Chemical Dictionary, a fairly ordinary word, a word that appears on nearly every page. What is not ordinary, what is in fact sufficiently far from ordinary to generate the specific kind of professional discomfort described above, is the rate at which 3I Atlas is producing it, and the ratio that production rate establishes relative to another molecule that serves as a chemical reference point. The instrument that made this measurement is ALMA, the Atacama Large Millimeter Array, a network of 66 radio telescope dishes spread across the Atacama Desert Plateau in northern Chile at an altitude of 5,000 meters above sea level, where the atmosphere is thin enough and dry enough to transmit the millimeter wavelength radio signals that molecular rotational transitions produce. ALMA is, in terms of its sensitivity to molecular signatures in space, the most powerful instrument of its kind ever built. It can detect the faint radio emissions produced when specific molecules rotate at their characteristic quantum frequencies, identifying chemical species and measuring their abundances with a precision that earlier generations of radio astronomers could not have imagined. When ALMA looks at a comet and measures its molecular output, the results are about as reliable as any measurement in observational astronomy. ALMA measured the methanol output of 3I Atlas relative to hydrogen cyanide. Hydrogen cyanide is used as a reference molecule in comet chemistry because it is reliably produced across a wide range of comet compositions and activity levels, making it a stable denominator against which to measure the relative abundances of other species. The methanol to hydrogen cyanide ratio in solar system comets spans a range that has been established across observations of dozens of objects over several decades of millimeter wave astronomy. That range runs from approximately 1 at the low end to approximately 20 at the high end, with most comets clustering in the middle portion of that range. The distribution is reasonably well understood in terms of the formation conditions and thermal histories of solar system comets. The ratio measured in 3I Atlas came in between 70 and 120. To be precise about what those numbers mean, the lowest end of the measured range for 3I Atlas, 70, is 3 to 4 times higher than the highest ratio ever measured in a solar system comet. The upper end of the range, 120, is 6 times higher than that previous record holder. 3I Atlas is not at the edge of the known distribution, slightly beyond the previously observed maximum in a way that suggests a continuous population extending further than the existing sample captured. It is in a different distribution entirely, separated from the solar system comet population by a gap wide enough to suggest that whatever produced this methanol abundance is not simply a more extreme version of the same process that produces methanol in solar system comets. It is either a different process, operating under different conditions, or the same process operating under conditions so extreme that they have no analogue in the objects we have previously studied. One solar system comet deserves specific mention as a point of comparison. Comet Linear, formerly designated C/2000/WM1, showed a methanol to hydrogen cyanide ratio at the upper end of the normal solar system range when it was measured in the early 2000s, generating modest scientific interest at the time as an unusually methanol-rich object. Linear's ratio was noted as high. Papers were written. The finding was accommodated within existing frameworks by invoking a formation region slightly enriched in carbon, relative to the average solar system comet source population. The community moved on. 3I Atlas is not in Linear's range. It is not close to Linear's range. If you plotted the methanol to hydrogen cyanide ratios of all measured solar system comets on a number line, and then plotted 3I Atlas on the same number line, there would be a visible gap between the highest solar system value and the lowest value measured for 3I Atlas. That gap is not a measurement uncertainty, it is a real separation in chemical space. Methanol production in comets is driven primarily by subsurface chemistry that accumulated over the formation history of the nucleus. When the comet approaches the Sun and solar heating penetrates into the subsurface layers, volatile rich material that has been chemically processing for millions or billions of years in cold interstellar environments begins to release its stored products. The methanol measured in Comet Comey represents a combination of methanol that was present in the original ices and methanol produced by chemical reactions triggered by the heating process itself. The observed ratio could, in principle, reflect a nucleus composition formed in an unusually carbon-rich region of the interstellar medium, where methanol precursors accumulated more efficiently than in the environments that produce typical solar system comets. But that explanation runs directly into the metallicity paradox that threads through this entire investigation like a fault line. If 3I Atlas formed in the early galaxy, as the deuterium enrichment strongly suggests, then carbon was scarce in its formation environment. The early Milky Way had not yet been seeded by multiple generations of stellar nucleosynthesis, with the carbon, oxygen and nitrogen that later epochs of galaxy evolution distributed through the interstellar medium. Extreme methanol production requires abundant carbon. Abundant carbon requires a formation environment that contradicts the deuterium signal. The two observations pull in opposite directions, and no currently published explanation fully resolves the tension between them. The episodic nature of the methanol release adds another layer of difficulty to the interpretation. ALMA's observations did not show a steady, gradually declining production rate of the kind expected from the progressive erosion of a volatile-rich surface layer as the comet approaches the Sun. Instead, the data showed methanol being released in bursts, spikes, in production rate that do not align cleanly with the object's rotation period in the way that surface-driven outgassing events typically do. Episodic outgassing is known in solar system comets. It occurs when cliff collapses expose fresh volatile material, when cracks propagate through the surface and open new pathways to subsurface reservoirs, when localized heating events trigger rapid sublimation from specific regions. These events are real and documented, but they produce outgassing patterns that are identifiably different from what the ALMA data shows for 3I Atlas. The spikes are too regular in their timing to be purely random surface events, and too irregular in their intensity to be cleanly periodic in the way that rotation-driven phenomena should be. One interpretation circulating in preprint literature involves internal heat sources driving subsurface chemistry independently of solar heating. Radioactive decay of isotopes within the nucleus generating enough thermal energy to trigger chemical reactions at depth, releasing products episodically as pressure builds and finds pathways to the surface. This mechanism is physically plausible for large cometary bodies with sufficient radiogenic material. Another interpretation involves electrical charging of the nucleus as it passes through regions of varying solar wind density and composition, with the electrical potential driving ion molecule reactions in the near-surface ices that produce methanol as a byproduct. This latter idea, sometimes called electrical processing of ices, sits well outside the mainstream consensus and has not yet received the kind of rigorous theoretical development that would make it testable against the existing data. What is not outside the mainstream, what is not speculative in any sense, is the measurement itself. The methanol ratio is what it is. ALMA measured it with the precision and reliability that makes its measurements the standard reference in molecular astrophysics. Measured anomalies have a specific property that speculative interpretations do not. They remain true regardless of whether the explanation catches up with them. The methanol ratio of 3I Atlas will still be between 70 and 120 long after every current interpretation has been revised, refined, or abandoned entirely. And it will still be sitting next to the nickel-ion anomaly in the same spectroscopic dataset, waiting for an explanation that accounts for both of them simultaneously, which, as it turns out, is considerably harder than accounting for either one alone. Part 8. The nickel-ion signature. In 2021, a pair of astronomers published a paper that quietly unsettled a field that believed it had a reasonably complete picture of comet chemistry. The finding did not make major headlines outside specialist circles. It did not trigger a scientific crisis or prompt emergency conferences, but among researchers who study the chemical composition of cometary comae, the diffuse clouds of gas and dust that surround active comet nuclei when solar heating drives off volatile material, the paper produced a specific kind of reaction. The slightly uncomfortable recognition that something assumed to be well understood was, in fact, less well understood than previously believed. The discovery was nickel. Specifically, nickel vapor detected in the comae of multiple solar system comets, not as trace contamination from a single unusual object, not as a marginal detection at the edge of instrumental sensitivity, but as a consistent and reproducible presence across a survey of dozens of comets observed by different telescopes at different times. Nickel, a dense transition metal sitting at atomic number 28 on the periodic table, most commonly encountered on Earth as a component of coins, stainless steel and various industrial alloys, was sublimating from comet surfaces and entering the gas phase at temperatures far lower than its known sublimation point in pure elemental form. This was chemically unexpected. Pure nickel does not sublimate at comet surface temperatures. The temperatures are simply too low by a large margin. For nickel to appear in the gas phase of a comet coma at the observed abundances, it had to be bound in some volatile carrier compound, a molecule that contained nickel as a component that sublimated at low temperatures and that then decomposed in the gas phase or under solar ultraviolet radiation, releasing the nickel atoms that the spectroscopic observations were detecting. The identity of that carrier compound was not immediately obvious, because nickel-bearing volatile molecules are not a well-populated category in astrochemistry. Eventually, a proposed mechanism involving organic nickel-bearing molecules, nickel carbonyl compounds and related species, gave the finding a theoretical home within existing frameworks. The mechanism was plausible, the chemistry was workable, and the initial discomfort gradually resolved into acceptance. Science does that. It absorbs surprises by extending frameworks rather than replacing them whenever extension is possible. The unsettling became manageable, the anomaly became a data point, and the field moved on, slightly wiser about what Comet Comey actually contain, and slightly more humble about the completeness of its previous inventory. 3I Atlas has a nickel signature too, but the ratio is wrong, and that wrongness sits in a different category from the mere presence of nickel in a comet coma. To understand why the ratio matters, you need the baseline. In the Sun, and in most solar system bodies that formed from the same primordial material as the Sun, the abundance ratio of iron to nickel follows a well-established pattern derived from the nuclear physics of stellar nucleosynthesis. Iron is roughly 18 times more common than nickel in solar abundance. This ratio is not arbitrary, it reflects the specific energy landscape of nuclear binding that makes iron 56 the most stable nucleus per nucleon. The endpoint toward which stellar nucleosynthesis tends to drive the production of heavy elements. Most solar system comets, when both iron and nickel are detected in spectroscopic data, show iron to nickel ratios that broadly reflect this cosmic baseline, with variations that fall within ranges attributable to the different formation histories and compositions of individual cometary bodies. The pattern is consistent enough to serve as a chemical fingerprint of solar system origin. In 3I Atlas, the nickel appears disproportionately abundant relative to iron. The measurements place the ratio outside the range established by solar system comets in a direction toward nickel enrichment that does not have an obvious natural explanation within the standard framework. The excess is not so large that iron disappears from the spectrum. This is not a case of a completely anomalous composition bearing no resemblance to solar system material. It is a case of a ratio being skewed in a specific direction by a specific amount in a way that requires a physical explanation that current models do not readily provide. Nickel-enriched material does occur in nature, both on Earth and in space, but in specific and contextually informative circumstances. On Earth, nickel enrichment relative to iron occurs in certain categories of industrial alloys, engineered for specific mechanical or chemical properties, stainless steel variants, superalloys used in aerospace and power generation, electro-deposited coatings. It occurs in specific types of iron-nickel meteorites, particularly those believed to represent the differentiated cores of disrupted planetesimals, where the pressure and temperature conditions of planetary core formation produced unusual mineral phases. In astrophysical environments, nickel enrichment can occur in the nucleosynthetic products of specific types of stellar explosions. Certain supernova subtypes produce nickel-56 as a primary decay product before it decays to iron-56, and the ratio of stable nickel to iron in the ejector depends on the timescale of observation relative to the decay. It can also occur, hypothetically, in unusual mineral assemblages formed under pressure and temperature conditions not commonly found in small solar system bodies. The uncertainty in interpreting spectroscopic measurements of gas plume composition is genuine and deserves explicit acknowledgement rather than dismissal. Cometary comae are not static, uniform chemical environments. They are dynamic systems in which the temperature, density, and chemical composition of the gas vary with distance from the nucleus, time of day on the rotating surface, distance from the Sun, and the activity state of specific regions on the nucleus at the moment of observation. The efficiency with which different compounds sublimate and enter the gas phase depends on all of these variables simultaneously. A measured ratio of nickel to iron in a coma spectrum represents a snapshot of a complex evolving system, and interpreting that snapshot as a direct reflection of bulk nucleus composition requires assumptions about the sublimation physics that introduce their own uncertainties. A skewed ratio could reflect a genuine bulk compositional anomaly present throughout the nucleus. It could also reflect a transient phase of outgassing, during which nickel-bearing compounds happen to be releasing more efficiently than iron-bearing ones, for reasons related to the thermal state of the surface at that particular moment. Researchers working on this measurement are appropriately cautious, and their caution is not evasion. It is the correct scientific response to a measurement whose interpretation depends on assumptions that are not yet fully validated. The nickel-to-iron anomaly is flagged in the literature. It is listed among the 22 irregularities that Loeb compiled in his systematic accounting of 3I Atlas anomalies. It is treated as a data point requiring explanation, not as evidence for any particular conclusion. No peer-reviewed paper currently in the published literature cites the nickel-iron ratio as evidence for anything beyond the range of unusual but potentially natural cometary chemistry. In less careful regions of the internet, the story has travelled considerably farther than the data supports. A nickel-iron anomaly in an object that also displays symmetric jets, unexplained transverse acceleration, an anti-tail that violates expected solar wind behaviour, deuterium ratios 10 times above the solar system baseline, and a Jupiter flyby precision that falls within 100,000 kilometres of the gravitational boundary has been described in various online forums and podcasts as a metallic signature consistent with engineered alloy structures, specifically with the kind of nickel-iron alloys used in spacecraft construction and structural materials designed for high-stress environments. That characterization is not supported by the data. The data establishes that the nickel-to-iron ratio in the observed coma spectrum is unusual relative to solar system comets. It does not establish the physical form of the nickel-bearing material, its location within or on the nucleus, the mechanism by which it entered the gas phase, or any connection to engineered materials of any kind. The leap from unusual spectroscopic ratio to manufactured alloy is not a small inferential step. It is a categorical jump across an evidentiary gap that the current data does not bridge. Open questions deserve careful answers. The history of science is populated with anomalous measurements that were eventually explained by previously unknown natural mechanisms, by new categories of molecules, new phases of matter, new physical processes operating in environments that our laboratory experience did not prepare us to anticipate. The nickel-iron anomaly in 3I Atlas may belong to that history. It probably belongs to that history. Probably is doing real work in that sentence, and being honest about the work it is doing is more useful than either dismissing the anomaly or inflating it beyond what the data supports. The convenient answers are abundant on both sides of this question. The careful ones are harder to construct and slower to arrive at, and none of the careful ones have yet addressed a geometric coincidence that most researchers consider too speculative to discuss in formal settings, and that none of them have been able to entirely stop thinking about in informal ones. It involves a line drawn between the arrival direction of this object and a specific point in the sky, a point that corresponds to the origin of a 72-second radio signal detected by a volunteer with a red pen in 1977. A signal that has never been detected again, and that has never been explained to the satisfaction of everyone who has studied it. The signal was called the WOW signal. And the geometry of what is happening right now is something that, once you know it, quietly refuses to leave you alone. Part 9. The WOW signal alignment. On the night of August 15th, 1977, a volunteer astronomer named Jerry Amon was doing something that sounds, by contemporary standards, almost meditative in its patience. He was sitting at a table reviewing paper printouts of data collected by the Big Ear Radio Telescope at Ohio State University. Long sheets of computer output representing the radio sky as a series of alphanumeric characters, each character encoding the intensity of the radio signal received from a particular patch of sky at a particular moment in time. The characters ran in columns. Low-intensity background noise produced single digits and low letters. A strong, narrow band signal would produce a sequence of higher characters climbing toward the letter U, which represented the maximum intensity the system could encode. Big Ear was part of the SETI project, the search for extraterrestrial intelligence, and had been scanning the sky since 1973, methodically sweeping through frequency bands near the hydrogen line, the radio frequency at 1.42 GHz emitted naturally by hydrogen atoms throughout the galaxy. Many researchers had argued, beginning with a landmark 1959 paper by Giuseppe Cocconi and Philip Morrison in the journal Nature, that the hydrogen line was the logical frequency for interstellar communication, a cosmic common ground, a channel that any technologically capable civilization would know about, because hydrogen is the most abundant element in the observable universe. If anyone was broadcasting, the reasoning went, they would broadcast near the frequency that every civilization capable of building a radio telescope would already be monitoring. For 4 years, Big Ear had found nothing. Thousands of hours of sky coverage, millions of data characters printed on thousands of pages. Nothing that stood out from the background in a way that could not be explained by natural, astrophysical sources or terrestrial interference. The work was patient, systematic, and almost entirely unrewarded by anything resembling a discovery. Eamon was reviewing one of these printouts when he encountered a column of characters that was different from everything surrounding it. The sequence was 6EQUJ5. In the encoding system Big Ear used, that sequence represented a signal that rose from background noise to a peak intensity 30 times above the baseline, held near that peak for the duration of the telescope's view of that sky position, and then fell back to background as the Earth's rotation carried the beam past the source. The signal was narrow-band, concentrated in a thin slice of the radio spectrum rather than spread across a wide range of frequencies, the way natural broadband sources behave. Its frequency was close to the hydrogen line. Its intensity profile was exactly the shape you would expect from a fixed-point source being swept through a radio telescope beam as the Earth rotates. A smooth rise to a peak and a smooth fall, symmetric, lasting precisely as long as the geometry of the observation predicted. Eamon circled the sequence in red pen and wrote one word in the margin next to it: wow. The signal lasted 72 seconds, the exact duration that a fixed radio source would remain within Big Ear's field of view, as Earth's rotation carried the telescope beam across the sky. It was detected once on that night from that sky position. It was never detected again. In the 47 years since August 15th, 1977, dozens of searchers have targeted the same region of sky using telescopes far more sensitive than Big Ear, covering a wider range of frequencies, employing detection algorithms incomparably more sophisticated than a volunteer with a printout and a red pen. None of them found a repetition. None found a related signal. None found anything that could be connected to what Eamon saw in that column of characters with enough confidence to declare the mystery resolved. Natural explanations have been proposed and debated across nearly 5 decades of analysis. Radio frequency interference from terrestrial sources was an early candidate, but the signal's characteristics, its narrow bandwidth, its frequency, its intensity profile, fit poorly with known interference patterns of the era. A team of researchers proposed in 2017 that the signal could have originated from hydrogen gas clouds surrounding comets, passing through the field of view, a mechanism that could produce a transient narrow-band signal at the hydrogen line frequency. The proposal attracted attention and some support, but also significant criticism from researchers who argued the cometary hydrogen explanation required conditions that were not well supported by the observational geometry of the night in question. The debate did not resolve. It added another layer to the mystery without removing the original one. The WOW signal remains, 47 years later, in a category that has no comfortable home in the taxonomy of either confirmed natural phenomena or confirmed artificial signals. It is a single detection, never repeated, never explained to universal satisfaction, never forgotten by anyone who has spent time with the numbers. It is the most anomalous result in the history of Radio SETI, and it sits in the literature like a splinter that the field has never quite been able to work out. Now draw a line. The arrival direction of 3I Atlas, the trajectory from which it entered the solar system, traced backward through the gravitational deflections of its journey to identify its point of origin in the sky, falls within approximately 9 degrees of the sky, coordinates associated with the WOW signal's source region. 9 degrees is not a precise match. Anyone claiming it is a precise match is overstating what the geometry shows. The positional uncertainty in the WOW signal's source is itself several degrees, because Big Ear's beam geometry at the time of detection did not allow for precise localization of the source within the beam. The arrival direction of 3I Atlas has its own uncertainties, smaller but not zero. The overlap is approximate, not exact, and yet approximate overlaps have statistical content. The sky is a sphere spanning 360 degrees in one angular dimension and 180 in the other. The total solid angle of the sky is approximately 41,000 square degrees. A circular region 9 degrees in radius covers approximately 254 square degrees, about 0.6% of the total sky. the probability that a randomly directed interstellar object would arrive from within 9 degrees of any specific target location, chosen in advance, is roughly 0.6%, approximately 1 in 160. 1 in 160. That sounds like a number worth paying attention to. It is also precisely the kind of number that statistics treats with the most caution, for reasons that are worth understanding carefully rather than either dismissing or inflating. The technical term for what happens when human brains encounter this kind of number is apophenia, the tendency to perceive meaningful connections between unrelated phenomena, to find patterns in noise, to assign significance to coincidences because the alternative, that they mean nothing, is psychologically unsatisfying in proportion to how striking the coincidence appears. Apophenia is not a flaw or a failure of intelligence. It is a feature of the human cognitive system that evolved in environments where pattern recognition was adaptive, where noticing the connection between rustling grass and the presence of a predator was more valuable than rigorously calculating the prior probability of that connection being causal. The brain that found patterns survived. The brain that demanded frequentist statistics before running generally did not. But the methodology that has produced everything humanity actually knows about the universe, from the motion of planets to the structure of DNA to the existence of gravitational waves, requires something more disciplined than pattern recognition. It requires that we ask not just whether a pattern exists, but whether the pattern was predicted before the data was examined or discovered after the fact. A prediction that precedes observation has statistical weight. A pattern noticed in existing data after the fact using a target that was not specified in advance has a different and much weaker statistical standing. We did not predict that 3I Atlas would arrive from near the WOW signal direction before its trajectory was known. We noticed the overlap after calculating the trajectory. That sequence, observation first, pattern recognition second, is the sequence that produces apophenia, not discovery. Post hoc pattern matching is how astrology works. It is not how science works. And yet the coincidence is real. The geometry is real. The number is real. And in the context of an object that has already accumulated 22 separate documented anomalies, an anti-tail that persists for months pointing toward the sun, jets in perfect triangular symmetry that remain stable through gravitational perturbation, deuterium ratios 10 times above the solar system baseline, transverse acceleration that the standard model handles awkwardly, a Jupiter flyby precision of 100,000 kilometers against a boundary 53 million kilometers out, placing one more coincidence on the pile, is something that intellectual honesty requires acknowledging, even while scientific discipline requires contextualizing it clearly. This is not evidence of a connection between the WOW signal and 3I Atlas. It is a geometric fact that, in the presence of so many other geometric and chemical and dynamical facts that resist easy explanation, a reasonable person might find it harder than usual to dismiss entirely. The WOW signal might have been a transient natural phenomenon that happened to mimic the expected profile of an artificial transmission closely enough to fool every researcher who has examined it for nearly 5 decades. 3I Atlas might be an unusual but entirely natural comet from the early Milky Way carrying chemistry that our models have not yet learned to accommodate. The spatial coincidence between them might be exactly what its raw probability suggests, a 1 in 160 alignment that carries no meaning whatsoever beyond the bare fact of its occurrence. Science demands this position as the starting point. The null hypothesis is always the mundane explanation, and the mundane explanation is always favoured until the evidence compels otherwise. But science also has a mechanism for testing null hypotheses. It is called observation, conducted with precision, with calibrated instruments, with pre-registered predictions and honest reporting of results regardless of which direction they point. And tomorrow, when 3I Atlas threads Jupiter's gravitational boundary at 53.6 million kilometers, the most powerful observational infrastructure in human history will be watching every photon it can collect from that object, looking for something that, if found, would make the conversation about null hypotheses considerably more difficult to continue. Some of those telescopes will be looking for something very specific, something that no natural comet, however ancient or chemically unusual, should be able to produce. And the researchers operating those telescopes are, for the most part, hoping very quietly that they do not find it. because finding it would mean that everything that comes next is a kind of science that none of them were trained for. Part 10, the fusion propulsion hypothesis. This is the part where we have to be the most careful. What follows is not a scientific conclusion. It is a thought experiment, a structured exploration of a speculative hypothesis that some researchers have discussed in informal settings and that certain preprint papers have outlined without endorsement from the broader community. It is presented here because it is the hypothesis that connects all of the previous anomalies into a single coherent framework. And coherent frameworks, even speculative ones, deserve to be examined rather than dismissed without examination. The hypothesis starts with deuterium. Deuterium is fusion fuel. This is not speculative. It is the basis of every serious fusion energy program on Earth. The deuterium-deuterium fusion reaction, and especially the deuterium-tritium reaction, releases energy at densities that make chemical combustion look like a birthday candle. That is why ITER, the International Fusion Reactor under construction in southern France, is designed around deuterium. That is why countries have spent hundreds of billions of dollars over 70 years trying to make it work. Fusion is the energy source of the stars. Deuterium is how you access it. An object carrying deuterium at 1% concentration, 50 times the ratio found in typical solar system comets, carries, if that estimate holds for its bulk composition, a quantity of fusion fuel that is genuinely extraordinary. The object's estimated mass, based on its brightness and outgassing rates, suggests a nucleus of perhaps a few kilometers in diameter. A few kilometer body of deuterium-enriched ice contains, in principle, an amount of fusion energy that would take our current civilization centuries to consume. Now comes the speculative structure. Some researchers have outlined models in which the anomalous features of 3I Atlas, the anti-tail, the jet symmetry, the transverse acceleration, the methanol overproduction, the nickel-ion ratio, could be interpreted as consistent with a magnetohydrodynamic propulsion system. Magnetohydrodynamic drives, or MHD drives, work by accelerating ionized plasma through magnetic fields. They require no moving parts, no conventional rockets. They produce directed jets of plasma. They can, in principle, be fed by fusion reactions. In this model, the anti-tail is not an optical artifact or a jet geometry anomaly. It is the exhaust plume of a system that vents processed material toward the sun as part of its propulsion cycle. The three symmetric jets are not randomly spaced active regions. They are intake or exhaust nozzles arranged for rotational balance. The transverse acceleration is not uneven outgassing, it is controlled maneuvering. The methanol excess is a reaction byproduct. The nickel-ion signature is structural alloy residue, and the Jupiter flyby precision is not a coincidence. It is a navigation event. The model is internally consistent. Every feature maps onto a function. That internal consistency is what makes it interesting as a thought experiment, and also what makes it dangerous as a conclusion. Post hoc models that explain all the data are not the same as models that predicted any of the data. Conspiracy theories are also internally consistent if you build them carefully enough. What separates speculation from science is testability, and this hypothesis is, at least in principle, testable. If 3I Atlas has onboard power generation, it should produce waste heat detectable in infrared wavelengths in excess of what solar heating alone can explain. If it has structured surfaces, radar, or high-resolution optical imaging at closest approach could detect non-random geometry. If its acceleration behavior changes in a discontinuous way, not gradual, as erosion produces, but sudden, as a controlled system might produce, orbital tracking would record it. Tomorrow's flyby puts the best telescopes in the world at their closest observing opportunity for this object. Whether anyone is specifically looking for signs of technology, rather than comet activity, is a question about scientific culture as much as scientific method. We are, as a species, genuinely unsure whether we are alone in the universe. We have never confirmed a signal. We have never found a structure. We have never detected a technology. That record is either because we are alone, or because we have not been looking carefully enough, or because what we are looking for does not look the way we expect. 3I Atlas may be an ancient comet from the early galaxy, with unusual chemistry and an improbable flyby distance. It may be the most interesting piece of ice ever to pass through our solar system. Or it may be something we do not have a word for yet. Either way, it is leaving. And after tomorrow, we will never have a better chance to know. Part 11. The Interstellar Visitor Explosion. For most of recorded human history, the possibility that objects from other star systems might pass through our solar system existed only as a theoretical footnote. The math allowed for it. The galaxy is enormous, stellar systems are numerous, and planetary formation is a violent enough process that ejecting material into interstellar space is not just possible, but essentially unavoidable. When young planetary systems form, gravitational interactions between growing planets act like cosmic slingshots, hurling smaller bodies outward at velocities high enough to escape the parent star's gravity entirely. Our own solar system did this. Jupiter's early orbital migration flung enormous quantities of material into deep space. The Oort cloud, that vast spherical reservoir of comets at the outermost edge of our solar system, is the population that almost escaped. The population that did escape is drifting through the galaxy right now. Yet for decades, the interstellar object detection count stood at a very clean and very unsatisfying number: 0. Not because researchers were not looking. Dedicated sky surveys have been scanning the solar system for fast-moving objects since the 1980s. The problem was sensitivity and coverage. The sky is enormous. Survey telescopes of earlier generations were slow, and interstellar objects pass through the inner solar system relatively quickly. The window for detection is narrow. An object moving at typical interstellar velocities spends only months in the region, bright enough and close enough to Earth to be found by the instruments we had. For decades, we simply missed them all. They came and went, invisible, carrying whatever they carried, leaving no record of their passage. Then, in October of 2017, a survey telescope in Hawaii called Pan-STARRS detected a fast-moving point of light on an unusual trajectory. Within days, orbital calculations confirmed what no instrument had ever confirmed before. The object, designated 1I/Oumuamua, the Hawaiian word meaning something like distant messenger arriving first, was not from our solar system. Its hyperbolic trajectory was too steep, its speed too high for any solar system origin. It had arrived from interstellar space, and it was already leaving. The scientific community's reaction was one of extraordinary interest and moderate caution. Oumuamua was small, perhaps a few hundred meters across, and tumbling in a way that made photometric measurements difficult. Its brightness varied by a factor of 10 as it rotated, implying a shape far more extreme than typical solar system asteroids or comets. The shape, inferred from those brightness variations, appeared cigar-like or possibly very flat, like a pancake or a thin disk. Neither shape is common among solar system small bodies. Elongated asteroids exist, but not at this ratio. Flat objects exist, but not naturally at this scale. Its colour was reddish, consistent with organic rich material processed by cosmic rays over long timescales. Everything about it was slightly off, and then, as it accelerated away from the Sun, it moved slightly faster than gravity alone could explain. The acceleration anomaly sparked a debate that is still technically unresolved. The leading natural explanation involves radiation pressure acting on an extremely low-density, highly reflective object, essentially a natural solar sail, a sheet of material thin enough that sunlight pushes it the way wind pushes a sail. The numbers work if the object is extraordinarily thin relative to its surface area. Another explanation invokes outgassing, the same mechanism that pushes comets off their purely gravitational trajectories when heated ice turns to gas and jets out from the surface. But no coma, no gas cloud, no emission of any kind was detected around Oumuamua, which is highly unusual for any active comet. Active comets announce themselves. Oumuamua was silent and still accelerating. Avi Loeb, the Harvard astronomer who would later compile 22 anomalies associated with 3I Atlas, made international headlines by suggesting that Oumuamua might be a fragment of alien technology, specifically a light sail, a propulsion device that uses radiation pressure intentionally rather than accidentally. He was careful to frame it as a possibility worth investigating rather than a conclusion. The mainstream scientific response was politely dismissive, which in academic culture is a specific kind of response. Not angry, not engaged, just quietly uninterested in pursuing the idea further. The debate was filed under unresolved, and the field moved on. 2 years later, Borisov arrived. 2I/Borisov was, in contrast to Oumuamua, reassuringly comet-like. It had a visible coma, the diffuse cloud of gas and dust that surrounds an active comet nucleus when solar heating drives off volatile material. It produced gas and dust at rates consistent with solar system comets. It had a colour and composition largely consistent with what we find in our own Oort cloud, with some interesting variations in its carbon monoxide content that suggested it formed in an unusually cold environment. Its trajectory was hyperbolic and clearly interstellar, but otherwise it behaved more or less as expected from a comet that simply originated around a different star. Borisov was the interstellar object that made researchers feel briefly that Oumuamua had been the strange outlier, the anomaly that proved the rule rather than broke it. That feeling of reassurance lasted until 3I Atlas arrived and declined to be reassuring about anything. The rapid succession of discoveries, 2017, 2019 and now the mid-2020s, is not just a catalogue curiosity or a pleasant progression in our detection capabilities. It is a signal about how common these objects are, about how much traffic is moving through the solar system that we have never been equipped to see, and about what we might have been missing for the entire history of human astronomy. Each discovery refined the statistical estimate of how many interstellar objects exist in the galaxy at any given time, and each revision pushed the number dramatically higher. The math is straightforward even if the implications are not. If 3 objects have passed through the detectable region of the solar system in roughly 8 years, and our current surveys only catch a small fraction of passing objects due to sensitivity and sky coverage limitations, the true population is enormous. Current estimates suggest that at any given moment, there may be several interstellar objects within the orbit of Neptune that we have simply not yet detected. They are there right now, drifting through the outer solar system, too faint or too fast or in the wrong part of the sky for our current instruments to catch. Over the full lifetime of the solar system, 4.6 billion years, billions of interstellar objects have passed through. They are not rare events glimpsed once in a generation. They are constant traffic. The solar system is not a quiet neighbourhood. It is a thoroughfare, and we have only just installed the first traffic camera. That change in perspective, from theoretical rarity to observed regularity, is one of the most significant quiet shifts in our understanding of the solar system in the past decade. It does not make headlines the way a new planet discovery does. It does not generate the public excitement of a Mars landing or a black hole photograph. But in terms of what it means for how we understand our place in the galaxy, the shift is profound. The solar system is not an isolated system drifting alone through empty space, sealed off from the rest of the universe by the vastness of the distances between stars. It is embedded in a continuous flow of material from other stars, other systems, other histories entirely. Pieces of planetary systems that formed billions of years ago around stars that no longer exist are passing through right now. Fragments of worlds we will never visit are briefly our neighbours. Some of that material carries chemistry we have never encountered in our own solar system. Some of it carries records of stellar environments that no longer exist anywhere in the observable galaxy, conditions from the early Milky Way, temperatures and densities that have not existed for 10 billion years, isotopic signatures that function like timestamps from the universe's youth, and some of it, based on what 3I Atlas appears to show, may carry surprises we're not yet equipped to categorize, not because our instruments are inadequate, but because our models did not predict anything like what we are measuring. The question is no longer whether interstellar objects pass through our solar system. That question was answered in 2017 and confirmed twice since. The question now is what they're carrying, where they came from, and whether the answer to either question will one day require us to revise something more fundamental than a chemistry model. Whether it will require us to revise our assumptions about what moves through interstellar space, and why, and whether all of it got there the same way. 3I Atlas is the third messenger. It arrived with fusion fuel, impossible jet symmetry, an anti-tail that defies the solar wind, and a flyby precision that made orbital mechanics researchers set down their coffee. It is the third data point in a sequence that is only just beginning to reveal its pattern, and the telescope that will give us the next 100 data points is almost ready to open its eyes. Part 12, the telescope that will find hundreds. Sitting on a mountain in northern Chile at an elevation of 2,800 meters above sea level, where the air is thin and the sky is almost offensively clear, a telescope is almost ready. The Vera C. Rubin Observatory takes its name from an astronomer who spent decades trying to convince a skeptical scientific establishment that most of the mass in the universe was invisible. Vera Rubin measured the rotation curves of galaxies in the 1960s and 70s and found something that did not fit. Galaxies were rotating as though they contained far more mass than the visible stars and gas could account for. The outer edges of galaxies were moving at speeds that should have flung them apart if gravity only came from what we could see. Rubin's measurements implied an enormous invisible component, what we now call dark matter, holding everything together. The establishment was slow to accept it. She was right. Naming the observatory after her is one of astronomy's more graceful acts of institutional acknowledgement, and the facility she lends her name to is designed to be exactly the kind of instrument that refuses to look away from inconvenient data. The Rubin Observatory is a facility unlike anything previously built for sky surveys. Its primary mirror is 8.4 meters across, large enough to collect light from extremely faint objects moving quickly across the sky, the kind of objects that earlier survey telescopes simply could not catch before they moved out of frame. Its camera is the largest digital camera ever constructed for astronomical use, 3.2 billion pixels, arranged across a focal plane the size of a dining table, capable of imaging an area of sky roughly 40 times the size of the full moon in a single exposure. To put that in perspective, most research telescopes image a patch of sky smaller than the full moon. The Rubin camera images 40 of those patches simultaneously, every time the shutter opens. Its computational infrastructure is built to match that ambition, processing tens of terabytes of raw data per night, running automated pipelines that flag new and moving objects within 60 seconds of each image being taken. Its mission, called the Legacy Survey of Space and Time, the acronym is LSST, which astronomers have already adopted as a word, is to photograph the entire visible southern sky every 3 to 4 nights for 10 consecutive years. Not once, not annually, every 3 to 4 nights for a decade. The result will be a time-lapse movie of the sky with a resolution and cadence that has never existed before. A record of everything that moves, flares, fades, appears, or disappears across the southern celestial hemisphere over a 10-year window. The Rubin Observatory is not specifically a search for interstellar objects. That would be underselling its ambitions considerably. Its primary science goals span some of the largest open questions in modern physics and astronomy. The nature of dark energy, the distribution of dark matter, the population of near-Earth asteroids that could pose impact hazards to our planet, the behavior of variable stars and transient phenomena like supernovae and gamma-ray bursts, the evolution of galaxies over cosmic time, and the demographics of our own solar system's small body populations. Interstellar object detection is an expected byproduct of those broader goals, a bonus output from a machine designed for bigger things. But the bonus has attracted attention that goes well beyond casual interest. Current projections, based on the detection rate established over the last decade and the enormous sensitivity improvements the Rubin Observatory represents over previous survey instruments, suggest that the telescope could detect somewhere between 10 and 50 interstellar objects per year. Read that again if you need to. Not per decade, per year. The same class of object that humanity detected 0 times before 2017 and 3 times in the 8 years since may be detected 10 to 50 times in a single calendar year once the Rubin Observatory reaches full operational capacity. Within the first few years of full operation, the catalogue of known interstellar visitors could grow from 3 to dozens. Within the full 10-year survey, potentially into the hundreds. That is not an incremental improvement. That is a phased transition in what the field knows and what it can ask. Consider what 3 known interstellar objects actually allow scientists to do. It allows them to say that interstellar objects exist and pass through the solar system. It allows them to note that one was very strange, one was relatively normal, and one is stranger still. It does not allow them to say whether any of those 3 is typical. It does not allow them to identify population trends, compositional patterns, size distributions, or trajectory clustering. 3 data points is enough to establish that something exists. It is not enough to understand it. With 50 or 100 interstellar objects in the catalogue, the situation transforms entirely. Statistical patterns become visible where before there was only anecdote. Researchers can ask whether chemical anomalies like the deuterium enrichment in 3I Atlas are common across interstellar visitors or unique to this object. They can ask whether acceleration anomalies occur at higher rates in interstellar objects than in solar system comets, and if so, what that implies about the mechanisms involved. They can ask whether the trajectories of interstellar objects are uniformly distributed across the sky, as you would expect if they come from random directions in the galaxy, or whether they show clustering towards specific regions, which would suggest preferred source directions or even source populations. They can ask whether the jet structures, the chemical compositions, the size distributions, and the flyby behaviours of interstellar objects form recognizable classes, the way solar system comets divide into short period and long period families based on where they come from. They can ask, in other words, whether 3I Atlas is the strangest thing the galaxy has sent through our neighbourhood, or whether it is merely the first one we looked at carefully enough to notice the strangeness. The Rubin Observatory will not answer the question of what 3I Atlas specifically is. Its detections will come after this object has left the solar system permanently, already beyond the range of meaningful follow-up observation, but it will provide the context in which that question can finally be properly framed. Right now, 3I Atlas is simultaneously the strangest and most studied interstellar object in the history of astronomy, and the only interstellar object displaying its specific combination of anomalies. Without comparison cases, without a population to compare it against, it is genuinely impossible to know whether its deuterium ratio, its symmetric jet structure, its persistent anti-tail, and its Jupiter flyby precision are unique properties of this specific object, properties that demand a specific explanation, or whether they are merely the first observed examples of behaviour that turns out to be common among interstellar visitors, behaviour that our models simply did not predict because we had never seen enough of them to know what to predict. 1 decade from now, that ambiguity will be substantially resolved. The Legacy Survey of Space and Time will have photographed the entire accessible sky more than 1,000 times across its survey period. Every interstellar object bright enough to register in its images, and its sensitivity threshold is dramatically lower than any previous survey, will be caught in the act of passing through, tracked across multiple observation epochs, and handed off to follow-up instruments for detailed characterization. The picture of interstellar object demographics that emerges will be richer and more detailed than anything the current generation of researchers can realistically imagine from where they stand today. If 3I Atlas turns out to be representative, if deuterium enrichment at 10 times the solar system baseline turns out to be common among interstellar visitors, if symmetric jet structures and unusual acceleration profiles turn out to be standard features of a class of objects the galaxy regularly produces, then the chemistry puzzle does not get easier. It gets harder and more urgent, because it implies that something about interstellar object formation or preservation produces these features routinely, in ways our current models completely fail to anticipate. The models need fundamental revision, not adjustment. If, on the other hand, 3I Atlas turns out to be a genuine outlier, the statistically strangest object in a catalogue of hundreds, displaying anomalies that no other interstellar visitor replicates, then the anomalies are not a modelling problem. They are a specific problem, requiring a specific explanation for a specific object. And specific explanations for specific anomalies in a single object are a different kind of scientific conversation than broad modelling revisions. The telescope will not ask what these objects mean. Telescopes do not ask questions. That remains an exclusively human activity. But the Rubin Observatory will give humans the data to pursue the meaning with the statistical rigour and comparative depth that the question deserves. And if the answer to what interstellar objects are, where they come from, and what they carry turns out to be something other than ancient comets with unusual chemistry, drifting randomly through the galaxy, if it turns out to require a revision more fundamental than a chemistry model, the Rubin Observatory will be the instrument that accumulated the evidence that made that revision unavoidable. But evidence alone does not power a civilization. Revision alone does not light a city. The next part of this story is about energy, specifically about the fuel that 3I Atlas appears to be carrying in extraordinary quantities, and the machines humanity is building right now in the hope of learning to use it. Part 13. The new generation of fusion reactors. There is a joke in fusion energy research that has been circulating for 70 years. Fusion power is always 30 years away, and it always will be. The joke has survived multiple generations of researchers, several rounds of government funding cycles, and at least 3 distinct periods when the field believed it was finally close. It is the kind of joke that people laugh at a little too hard at conferences because it contains a specific kind of pain, the pain of a goal that keeps receding as you approach it. like a mirage above hot pavement. The joke acknowledges something real. The field has been chasing a goal of extraordinary difficulty for longer than most scientists' entire careers. But it slightly obscures something equally real, something the most recent data makes harder to dismiss. The distance between the joke and the reality has been closing, and in the last 5 years it has been closing faster than at any previous point in the history of the field. Fusion is the process that powers the sun. It is, in the most literal sense, the reason anything exists in a form complex enough to wonder about it. Two light atomic nuclei, most efficiently, two isotopes of hydrogen, collide with enough energy to overcome their mutual electromagnetic repulsion, approach close enough for the strong nuclear force to take over, fuse together into a heavier nucleus and release energy. They release energy because the combined nucleus weighs slightly less than the sum of its components. That missing mass does not disappear. It converts directly into energy, according to the relationship encoded in the most famous equation in physics. The amount of energy released per unit of fuel mass is approximately 10 million times greater than the energy released by burning the same mass of chemical fuel. Stars do this continuously, sustained by the gravitational pressure of their own enormous mass compressing their cores to conditions of extreme density and temperature that no terrestrial environment can naturally replicate. The core of the Sun operates at approximately 15 million degrees Celsius, and pressures roughly 250 billion times higher than Earth's atmospheric pressure at sea level. Under those conditions, hydrogen nuclei fuse constantly, releasing the energy that has warmed our planet for 4.5 billion years. The Sun is, in the most practical sense, a fusion reactor. It is just a fusion reactor that uses gravity as its confinement mechanism, and gravity at that scale requires a mass of approximately 2 times 10 to the power of 30 kilograms to achieve. We cannot build that on Earth. We have to find another way to hold the plasma together long enough and hot enough for fusion to occur. On Earth, we use either magnetic fields or lasers. The magnetic approach, called tokamak design from the Russian acronym for the device configuration, has dominated government-funded fusion research for decades. A tokamak uses powerful superconducting magnets arranged in a toroidal donut-shaped configuration to contain superheated plasma in a magnetic bottle, preventing the plasma from touching the reactor walls and losing energy. The engineering challenge is immense. Plasma at fusion temperatures is inherently unstable, prone to turbulent fluctuations that can disrupt confinement and quench the reaction. Maintaining stable confinement long enough for net energy gain has been the central engineering problem of the field since the 1950s. The largest tokamak ever built is ITER, the International Thermonuclear Experimental Reactor, currently under construction in Cadarache in southern France, in a facility that occupies roughly 180 hectares and involves the coordinated manufacturing efforts of industries across 35 participating nations. The project is funded by a consortium representing the European Union, the United States, China, Russia, India, Japan, and South Korea, nations representing more than half the world's population, agreeing on at least this one thing. Its construction cost has grown over the decades of planning and building to approximately $22 billion, making it one of the most expensive scientific facilities ever attempted. ITER is designed to produce 10 times more energy than it consumes, the milestone expressed as Q equals 10, where Q is the ratio of fusion energy output to the energy input required to heat and sustain the plasma. No tokamak has ever achieved Q greater than approximately 0.67, a result set by the Joint European Torus in 1997 that stood as the record for over 2 decades. ITER is designed to shatter that record by a factor of 15, using a plasma of deuterium and tritium, 2 isotopes of hydrogen, heated to temperatures exceeding 150 million degrees Celsius. That is roughly 10 times hotter than the core of the Sun, which achieves fusion through pressure rather than temperature. On Earth, with no gravitational compression available, you compensate by going hotter. ITER is not a power plant. It produces no electricity for any grid. It is a proof of concept, a machine designed to demonstrate that controlled fusion at Q equals 10 is physically achievable, clearing the way for the generation of devices that will follow. The next step in the official roadmap is DEMO, the demonstration power plant, which will be the first fusion device designed to actually generate electricity and deliver it to consumers. The most optimistic current timelines place demo operations somewhere in the mid-2040s. The less optimistic timelines do not differ dramatically, because the engineering challenges between ITER and demo are well understood, even if not yet solved. But the official government roadmap is no longer the only roadmap. Private fusion investment has undergone a transformation in the past decade that would have seemed implausible to anyone who lived through the lean funding years of the 1990s and 2000s. Venture capital, technology billionaires, and institutional investors have collectively poured billions of dollars into fusion startups, pursuing designs and timelines that government programs considered too aggressive to fund. Commonwealth Fusion Systems, a spin-off from MIT, is building a compact tokamak called Spark, using high-temperature superconducting magnets that achieve field strength previously impossible, enabling a much smaller and potentially faster path to net energy gain. Helion Energy has raised billions with a design that claims a path to electricity generation, not just heat production, by the early 2030s. TAE Technologies is pursuing a different plasma configuration entirely. National Ignition Facility at Lawrence Livermore, using the laser confinement approach rather than magnetic, achieved fusion ignition, more energy out than laser energy in December of 2022, the first time that milestone had ever been crossed. The joke is aging. It is not yet dead, but it is looking less comfortable than it used to. The fuel for most of these designs is deuterium. In some designs, deuterium is paired with tritium, a radioactive isotope of hydrogen that does not occur naturally in significant quantities and must be bred from lithium inside the reactor itself. In others, including some of the more advanced private designs, deuterium-only reactions are the target, which would eliminate the tritium breeding requirement entirely and simplify the fuel cycle considerably. Either way, deuterium is the foundation, and deuterium, it turns out, is not scarce by any terrestrial standard. It is present in seawater at a concentration of approximately 1 part in 6,400 by number of atoms, modest but distributed across every ocean on Earth. The total deuterium content of Earth's oceans, if extracted and used as fusion fuel, could supply the entire current global energy consumption for millions of years. The ocean is, in the most literal sense, a nearly inexhaustible fuel reservoir for a post-carbon civilization. We simply need to learn how to burn it. What makes the deuterium content of 3I Atlas interesting in this context is not that we need to import it from an interstellar comet. We do not, and the logistics of that idea do not survive contact with orbital mechanics. What makes it interesting is the concentration, and what that concentration implies about the process that produced it. A deuterium to hydrogen ratio of approximately 1% means that some natural physical and chemical process, operating in conditions of extreme cold, over timescales measured in billions of years, in an environment that no longer exists anywhere in the observable galaxy, produced, preserved, and delivered a deuterium-enriched body across interstellar distances to our doorstep. Whatever that process was, it achieved an enrichment factor that our most sophisticated isotopic separation technologies would struggle to match efficiently. The object is, in some sense, an existence proof that nature can manufacture concentrated fusion fuel without any engineering at all, using nothing but time, cold, and chemistry. Understanding how it did that, the specific formation environment, the preservation mechanism that kept the enrichment intact across billions of years and light years of travel, the transport pathway that directed it here might or might not inform anything practical about how we generate fusion energy on Earth. The connection is more poetic than technical. Nature's method involves timescales and temperatures we cannot access in any laboratory. But the timing sits differently when you hold it at arm's length and look at it honestly. Humanity is, at this precise moment in history, on the threshold of making fusion power work, not in 30 years, potentially in 10. And at this precise moment, an object saturated with fusion fuel at concentrations no solar system body has ever matched is threading Jupiter's gravitational boundary for the first and last time in all of human history. Maybe that is a coincidence. This entire story is full of coincidences. The question is whether coincidences accumulated in sufficient number eventually require a different name. Part 14. AI is now searching for alien technology. When SETI began in 1960, the search strategy was defined entirely by the instruments and methods available at the time, and those instruments and methods were, by contemporary standards, almost touchingly modest. Frank Drake pointed a radio telescope at 2 nearby sun-like stars for a total of about 150 hours and listened. He heard nothing artificial. He called the project Ozma after the Queen of the fictional land of Oz, a place he noted that was very far away and very difficult to reach. The name was apt in ways Drake probably did not intend. The search for extraterrestrial intelligence has always been, at its core, a search conducted at the boundary between science and imagination, between rigorous methodology and the oldest question our species has ever asked. Radio telescopes listened to the sky. Researchers looked for narrow-band signals, transmissions compressed into a very thin slice of the radio frequency spectrum, with high information content that natural astrophysical sources could not easily produce. Natural radio sources are generally broadband. They spread their energy across wide ranges of frequency, produced by physical processes like synchrotron radiation or thermal emission that do not preferentially concentrate power into narrow channels. A narrow band signal of high intensity would therefore stand out against the natural background the way a laser pointer stands out in a darkened room, not because it is brighter than the sun, but because it is concentrated in a way that diffused natural light is not. The approach was patient, systematic, and manually intensive. Astronomers reviewed data printouts. They listened to recordings of radio telescope output converted to audio. They wrote notes in the margins. The WOW signal, the strongest anomalous signal in the history of SETI, detected in 1977 and never explained, was found by a volunteer named Jerry Eman, reviewing paper printouts with a red pen, who circled a sequence of characters and wrote one word next to it that became the name of the most famous unresolved mystery in radio astronomy. That was 65 years ago. The question has not changed. The tools available to investigate it have become completely unrecognizable. Modern sky surveys generate data volumes that no human researcher, or team of human researchers, or institution of human researchers working in coordinated shifts around the clock could meaningfully review by hand. The Rubin Observatory, when fully operational, will produce on the order of 20 terabytes of raw image data per night. 20 terabytes every night for 10 consecutive years. The Square Kilometre Array, the next-generation radio telescope currently under construction across 2 continents, with antenna arrays distributed across the remote interior of South Africa and the outback of Western Australia, will, when complete, generate data at rates that exceed the entire traffic of the current global internet, not the traffic of a single country, not the traffic of a major city's telecommunications infrastructure, the entire global internet in data volume per unit time. That is the scale at which the next generation of astronomical instruments will operate. In this environment, manual review is not slow. It is not inefficient. It is not something that could be improved with more staff or better organization. It is simply impossible, in the same way that counting individual atoms in a glass of water is simply impossible. Not a practical challenge, but a categorical one. The only tools capable of processing data at this scale are machine learning algorithms, and the field of astronomical data analysis has spent the last 15 years building, training, and deploying them at accelerating pace. 2 categories of algorithms have become particularly important. The first category is trained to find patterns that humans specify in advance. A researcher who suspects that certain types of variable stars follow specific brightness curve shapes can train a neural network on known examples of those shapes and deploy it across millions of light curves to find candidates. The network does efficiently and continuously what a human expert would do slowly and occasionally. The second category is more interesting and more unsettling in its implications. These algorithms are trained not on specific patterns, but on the general properties of a known population, and they flag objects that fall outside that population in ways that were not anticipated. They find what humans did not know to look for. They identify the anomaly before the anomaly has been named. Machine learning has been applied to CT explicitly since the mid-2010s, with sophistication that has accelerated alongside the broader revolution in artificial intelligence. Neural networks trained on comprehensive catalogues of natural radio sources, pulsars, quasars, masses, supernova remnants, can flag incoming signals that deviate from every known natural class above a specified statistical threshold. Convolutional neural networks can analyze telescope images for structural regularities that human visual inspection might miss, geometric features, bilateral or rotational symmetries, non-random spatial arrangements in the distribution of light. Time series algorithms can identify unusual patterns in the brightness curves of stars that might indicate large structures passing in front of them. Structures whose transit profiles differ from planetary transits in ways that suggest non-spherical, non-random geometries. None of these tools announce a discovery. They flag a candidate. They produce an output that says, in quantitative terms, this object or signal deviates from the known natural baseline by this many standard deviations across these specific metrics. What that deviation represents is then a question for human judgment, human follow-up, human interpretation. The algorithm identifies the anomaly. The scientist decides what the anomaly means. The application of these methods to interstellar objects is newer than their application to signals and stellar phenomena, but it has been developing quickly and with considerable urgency since Oumuamua forced the field to confront the possibility that anomalous fast-moving objects might reward careful algorithmic scrutiny. Following the controversy surrounding Oumuamua's unexplained acceleration, several independent research groups began developing algorithms specifically designed to analyze the photometric brightness curves, non-gravitational acceleration profiles, and spectral signatures of fast-moving solar system objects for features that are statistically inconsistent with natural comet or asteroid behavior. These are not algorithms that search for explicit signs of technology. Technology is not a category that can be directly encoded into a training set, because we have no confirmed examples of extraterrestrial technology to train on. Instead, these algorithms search for statistical outliers, objects where the best available natural model fails to fit the observed data above a confidence threshold that the researchers specify in advance. The outlier flag does not say artificial. It says unexplained by known natural mechanisms, and it does so with a quantified level of confidence. 3i Atlas has been run through several of these algorithms by multiple independent research groups. The results have not been publicly released in peer-reviewed form as of the time this is being written. That absence of publication does not mean the results are negative, and it does not mean they are being suppressed. It means the analysis is ongoing. The peer review process takes time, and researchers working on genuinely sensitive scientific questions tend to be careful about releasing preliminary findings that could be misinterpreted by a public that is, entirely understandably, primed to find this story significant. What has been confirmed, through statements from multiple research groups in conference presentations and informal communications, is that the object scores anomalously across several of the metrics these systems are designed to measure. Not on one metric, not on a marginal deviation from baseline, anomalously across several metrics in an object that was already anomalous by every conventional measure before any algorithm touched the data. Anomalous does not mean artificial. This distinction matters enough to state it plainly and more than once. An anomalous score means the object's observed characteristics deviate from the trained natural baseline in ways that the algorithm identifies as statistically significant and flags for human review. It means the natural model is struggling with this object in a quantifiable way. It does not mean the natural model is wrong, or that the deviation has no natural explanation, or that anything about the object was designed. Science has a long and productive history of anomalous results that eventually received natural explanations that simply required model revision. The history of astronomy is, in some ways, a history of anomalies that turned out to be new categories of natural phenomena rather than evidence of anything beyond nature. Human review in this case means the most sophisticated observational infrastructure in human history, the James Webb Space Telescope, the Hubble Space Telescope, the ALMA radio array, ground-based optical observatories on multiple continents, all simultaneously pointed at a single object and collectively asking a question that the scientific community is very careful about asking out loud in formal settings, even as it is asked freely in private conversations, in hallway exchanges at conferences, in the kind of candid speculation that happens when the recording devices are off. Are we looking at something that was made? The answer, in all currently available evidence, is no. Not confirmed, not supported, not demonstrated by any finding that has passed peer review and achieved community consensus. The mainstream scientific position is that 3i Atlas is an unusual comet with several features that current models handle poorly, and that unusual comets with poorly handled features are scientifically interesting without being scientifically revolutionary. That is a legitimate position. It is defensible. It is grounded in appropriate epistemic caution, and in the real and important principle that extraordinary claims require extraordinary evidence, and that the evidence currently in hand, while genuinely strange, does not yet clear that bar. But science is not a vote, and it is not a position that gets locked in place by the weight of current consensus. It is a process driven by data, constrained by evidence, and obligated to follow both wherever they lead, regardless of how inconvenient the destination turns out to be. And the process is not finished. Tomorrow, the object makes its closest approach to Jupiter. The telescopes are aligned, the instruments are calibrated, the algorithms are running. Every measurement taken in the next 72 hours will either add another data point to the list of anomalies that natural models struggle to accommodate, or offer an explanation that resolves some of the existing tensions and brings the object back within the boundary of the explainable, or, in the scenario that no official body is publicly anticipating, and that everyone working closest to the data is privately unable to stop thinking about, produce something that requires a different kind of conversation entirely. The kind of conversation that starts with a single, quiet, irreversible sentence and changes everything that comes after it. Part 15. What happens tomorrow? The countdown is real. At some point in the next 24 hours, depending on when you're reading or hearing this, 3i Atlas will reach its closest approach to Jupiter. The moment will pass without ceremony in any public square or news broadcast. There will be no live coverage on the major networks, no breaking news Chiron, no press conference with the director standing at a podium in front of a NASA logo. The object will silently thread the gravitational boundary at 53.6 million kilometers, continue its hyperbolic arc through the outer solar system, and begin the long sunward recession that will eventually carry it back into interstellar space, back into the dark between the stars, back into the galaxy from which it came, and from which nothing we currently possess could ever retrieve it. From that moment, the window begins to close. Not dramatically, not all at once, but with the quiet and absolute certainty of physics. Each day that passes after closest approach, the object moves farther from Earth. The apparent brightness in telescope images decreases. The angular resolution of the nucleus degrades. The signal-to-noise ratio in spectroscopic measurements, the ratio of real information to background noise, falls as the distance grows and the reflected and emitted light spreads thinner across space. Each week, the pool of instruments capable of contributing meaningful new data shrinks. Each month, the questions that could theoretically have been answered with another observation become questions that cannot be answered at all, because the object is too far, too faint and moving in the wrong direction. Within perhaps 2 years, it will be beyond the effective range of all but the most dedicated and powerful deep sky monitoring programs. Within a decade, it will have crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, and left our solar system permanently. It will be gone in every practical sense of that word. Whatever we do not learn in the next few months will be inaccessible to us forever. Not for a generation, not until better telescopes are built. Forever, because the object itself will be unreachable and unobservable, carrying its answers with it into a darkness we cannot follow. So what are the telescopes actually watching for in the hours and days surrounding this flyby? The most physically straightforward prediction involves changes in outgassing behaviour, triggered by the gravitational influence of Jupiter itself. Even at 53.6 million kilometres, a distance greater than a third of the distance between Earth and the Sun, Jupiter's gravity is not trivial. It creates tidal forces across the body of the nucleus, differential gravitational pulls that stress the material from one side to the other. If 3i Atlas has the structural properties of typical cometary bodies, loosely consolidated aggregates of ice and dust, sometimes described as rubble piles held together more by self-gravity and ice bonding than by any intrinsic material strength, those tidal stresses could fracture surface layers, crack open new pathways to subsurface volatile reservoirs, and change the geometry of active regions in ways that would show up immediately in the jet structure. If the three-jet pattern shifts during or after the flyby, if new jets appear, if existing jets change their orientation, if the triangular symmetry breaks down under tidal perturbation, that tells us something specific and important about the structural integrity of the nucleus. Loosely consolidated cometary material responds to tidal stress in predictable ways. The response, if observed, constrains the model. If the jet pattern does not change, if the three-jet structure persists through the Jupiter flyby, with exactly the same geometry it has maintained for the months of observation preceding it, unmoved by the closest gravitational perturbation the object will ever experience in our solar system, that tells us something different and something considerably harder to explain within the standard cometary framework. It would suggest that the structural properties of the nucleus are highly resistant to perturbation, either because the material is unusually strong and coherent, or because the jet geometry is maintained by a mechanism that does not depend on surface topology in the way normal cometary jets do. A mechanism that is, in other words, not sensitive to tidal forces in the way that volatile-driven sublimation jets should be. Either outcome constrains the models. Neither outcome is uninformative, but one of them is much easier to accommodate than the other. The acceleration measurement during and after the flyby is equally critical and in some ways more sensitive to the underlying physics. Orbital mechanics teams at multiple institutions are tracking the trajectory of 3I Atlas with the highest precision their instruments allow, using astrometric measurements from multiple observatories to pin down the object's position and velocity to extraordinary accuracy. The gravitational assist from the Jupiter flyby, the change in velocity that results from the object passing through Jupiter's gravitational field at this distance, is predictable from classical mechanics to within very small uncertainties. After the flyby, the trajectory should reflect that precisely calculable gravitational kick, plus any non-gravitational acceleration that was already present before the encounter. If the post-flyby trajectory deviates from that prediction, if there is residual acceleration beyond what the gravitational model plus the pre-existing non-gravitational component would produce, that deviation carries direct information about its source. If the non-gravitational acceleration changes in character during or after the flyby, not just shifting in magnitude, as gradual outgassing changes would produce, but shifting in direction or changing abruptly rather than gradually, the discontinuity is a fingerprint. Continuous natural processes produce continuous acceleration profiles. Discontinuous changes require discontinuous causes. Radio observations are continuing around the clock. The SETI Institute's monitoring protocols, which have evolved considerably from the early days of manual printout review, now include specific search parameters and filtering algorithms designed for signals associated with objects on known hyperbolic trajectories, objects moving through the solar system on paths that do not originate within it. 3I Atlas has been on a continuously monitored trajectory for long enough that if it had been transmitting any radio signal at a power level detectable by current instruments in the directions of Earth or major radio observatories, that signal would in all likelihood already have been identified. No such signal has been reported. It is important to say clearly what that means and what it does not mean. It is evidence against continuous directed radio transmission at detectable power levels. It is not proof that no signal exists. A transmitting object might be directional rather than omnidirectional, broadcasting toward a target that is not Earth. It might transmit intermittently rather than continuously. It might use frequencies or modulation schemes outside the parameter space being searched. The absence of a detected signal is a constraint, not a conclusion. Infrared observations are perhaps the most physically diagnostic measurements being taken because they speak most directly to the question of internal energy. Every object in the solar system absorbs solar radiation and re-emits it as heat. The temperature of a passive icy body at a given distance from the Sun is predictable from basic thermal physics. It depends on the object's reflectivity, its rotation rate, its thermal conductivity, and the solar flux at its location. If the measured infrared emission from 3I Atlas exceeds what that thermal model predicts, the excess requires an internal heat source. Radioactive decay of short-lived isotopes within the nucleus can produce internal heat in large cometary bodies. This is a known, natural mechanism that has been studied in the context of early solar system planetesimal evolution. But radioactive heating has predictable limits and predictable timescales. Excess infrared emission beyond what radioactive decay could plausibly produce would require something else. The James Webb Space Telescope, which has already delivered the deuterium measurements that opened this entire investigation, is capable of detecting temperature anomalies at this range with sensitivity that no previous infrared observatory could match. If the excess is there, Webb will find it. And then there is the question that does not appear in any formal observation proposal, that no principal investigator has written into any telescope scheduling request, that no funding agency has officially prioritized, And yet the question that everyone working closest to this data carries with them at some level, in some form, whether they acknowledge it openly or not. What if something changes in a way that was not predicted? Not a gradual evolution of outgassing consistent with surface erosion. Not a slow procession of jet orientation consistent with a changing rotation state. Something discontinuous. Something that does not fit any of the model categories being tested. Something that looks, in the data, like a response, like an adjustment, like a decision. That question lives in a category that science does not yet have official procedures for handling, and yet it is precisely that question, unspoken, unofficial, slightly embarrassing in its implications, that makes every other aspect of this story matter to people who would not otherwise spend an evening thinking about orbital mechanics. We're not just tracking an unusual comet with anomalous chemistry and poorly explained structural features. We are living through a specific and unrepeatable moment in which the oldest question our species has ever asked, are we alone?, is being investigated not with radio telescopes pointed hopefully at distant stars, but with every instrument we possess pointed at something that is right here, right now, close enough to characterize in detail, behaving in ways we cannot fully explain, and leaving in a matter of months. The universe has always been old, strange, and completely indifferent to whether we understand it. Most of the time, that indifference is manageable. There are enough problems on the third planet from the Sun to keep any civilization occupied indefinitely. But occasionally something passes through the neighborhood, and the indifference starts to feel less like a background condition, and more like a challenge. More like a test that has been quietly administered to every technological civilization in the galaxy, at some point in its development, to see whether it was paying attention when the answer came close enough to touch. 3I Atlas is either the strangest natural comet ever observed, a relic of the early galaxy carrying chemistry that challenges our models of planetary formation, isotopic fractionation, and interstellar transport, interesting and important and ultimately explainable within a framework we have not yet fully developed, or it is something we do not have a framework for yet. Something for which the frameworks will have to be built after the fact, once the data forces the construction. Tomorrow the telescopes look, the data comes back, and whatever that data says, whether it is ordinary or extraordinary, expected or completely without precedent, whether it resolves any of the 22 anomalies or adds to them, we will have been the species that was here when this happened. Looking, asking, refusing to accept that the universe keeps its secrets without a fight, even when the fight is asymmetric and the universe has a considerable head start. The object is 53.6 million kilometers from Jupiter's gravitational boundary. It arrived from a direction in the sky within 9 degrees of the oldest unexplained signal in the history of radio astronomy. It carries fusion fuel at isotopic concentrations no solar system comet has ever matched. It accelerates in ways the standard model accommodates awkwardly. It has 3 jets arranged in perfect triangular symmetry that have held their geometry for months. It has an anti-tail that points toward the Sun and that nobody has fully explained. And it threaded Jupiter's gravitational boundary with a precision that made orbital mechanics researchers, who are not given to dramatic reactions, quietly set down their coffee. It is leaving. And when it is gone, when the last telescope loses it in the noise, when the last data point is recorded, when the window closes and the question becomes permanently unanswerable for this particular object, the question it leaves behind will be exactly the same question it arrived with, just heavier than it was before and considerably harder to put down.